Hello everyone, I am Rajapriya, working as Assistant Professor in the Department of Civil Engineering at National Engineering College, Kovilpatti. In this video, we are going to discuss about the energy principle concept in the Strength of Materials course. Before moving into the concept, we'll first discuss what is called strength of materials and why it is needed in civil engineering course. Strength of materials is a course which deals with the behavior of solid materials when they are subjected to some kind of external forces. So this is important in civil engineering since we deal with different elements, different structural elements, and we have to study the behavior of such elements when they are subjected to external forces. Let's move on to the concept of energy principles. These are all the contents which I am going to discuss in this video. So the first one is about the elastic strain energy, and next the terms and the terminologies related to the strain energy. Next one is the strain energy due to gradually applied loading condition. So we'll see the first one, which is strain energy. Strain energy is an energy which is stored in a body when it is subjected to some kind of external loading within the elastic limit. So when a material is subjected to external loading, either it may be a gradually applied load, suddenly applied load, or impact load, but it should be within the elastic limit, and due to the application of the load, the body deforms so that some work is done on it. During that time, the body will store some energy. So this stored energy is called as the strain energy. I have mentioned that the loading may be gradual, sudden, or impact loading. So the difference between sudden and impact load is that impact load is a load which is applied from a height. So when a load is dropped from a certain height, it is called as impact load. So we'll see what is the strain energy stored in a body due to these three different kinds of load. The strain energy concept can be better understood by this bow and arrow example. So it is a solid material. The molecules in the solid materials would be held together by the intermolecular forces. To deform a solid material, some work has to be done. In this case, when we pull the string, the bow bends. So what happens to the molecules inside the bow materials? They get rearranged and they store some energy. This stored energy is called as strain energy. What happens because of the stored energy? This energy gets transferred to the arrow in the form of kinetic energy, and only because of which the arrow propels. This is an example to understand the strain energy concept. Strain energy will always be equal to the work done to deform the body. Both will always be equal. The work done will be equal to the work stored. The stored work is called as the strain energy. We have certain terms related to the strain energy. The first one is the resilience. Resilience is the total strain energy which is stored in a body. In this graph, which is plotted stress versus strain, in this graph we can see the elastic limit is here. The resilience will be the total strain energy which is stored in the body. So resilience can be anywhere within the elastic limit. Next one is proof resilience. The next term is proof resilience. So it is the maximum strain energy which is stored in a body. The maximum strain energy will be at the elastic limit. So the proof resilience will be the maximum strain energy and the resilience will be the total strain energy within the elastic limit. And here you can see the mathematical expression for the strain energy here, which is sigma square by 2E into V. This expression we'll see in the upcoming slides. And the next term is called as the modulus of resilience. So the modulus of resilience can otherwise be called as the proof resilience per unit volume. Proof resilience is the maximum strain energy which is stored in the body. Hence modulus of resilience will be maximum strain energy per unit volume. And this is the mathematical expression for modulus of resilience. And remember that strain energy would be stored only in the elastic region up to the elastic limit. Next term is strain energy density. It is the strain energy per unit volume. And strain energy density can be expressed as U by V. There is a strain energy by unit volume. Next one is, this next concept is strain energy due to gradually applied loading. So the load is applied gradually. If the load is applied gradually, what is the strain energy which is stored, which would be stored by the solid material? So for that, we consider a bar of length L and cross-sectional area A. It is subjected to a load P. Because of that load, it is subjected to a change in the length, which is delta L, or the deflection or the deformation produced is termed as delta L. Sigma will be the stress which is induced in the bar. The stress may be either a tensile stress or compressive stress based on the load. And E will be the modulus of elasticity or the Young's modulus. Since we consider within the elastic limit, we are taking Young's modulus into account. And this is the load versus extension or the deformation diagram. The load is applied gradually and this will be the strain energy which is stored. This is the load versus deformation diagram in case of gradually applied loading. And this is the resistance versus deformation diagram in case of gradually applied loading. Work done on the bar. So here we are doing the work on the bar of length L. So the work done will be equal to the area of the load deformation diagram. Since it is a triangular pattern, the area will be half into P into delta L. So this will be the work done on the bar and this is taken as equation number 1. And equation number 2 will be work which is stored in the bar, which is based on this resistance versus deformation diagram. So the work stored in the bar will be equal to area of the resistance deformation diagram. Since it is also a triangular pattern, the area will be half into R into delta L. Load is defined as P and the resistance is defined as R. So R will be equal to stress into area. Since stress is equal to load by area, resistance or the load will be stress into area, and this is taken as equation number 2. Now we have already seen that work done will be equal to work stored. So equating 1 and 2, 1 is half P into delta L and 2 is half sigma into A into delta L. And this we have seen, P is stress into area and stress is equal to load by area since the load is applied in a gradual manner. Strain energy is nothing but the work stored. So which is half R into delta L. R is sigma into A. And we can again I express this delta L in terms of epsilon into L. The epsilon is strain. Strain is equal to change in length by original length. So change in length will be strain into length, and again the strain can be expressed in terms of Young's modulus. Young's modulus is nothing but stress by strain. So strain will be equal to stress by Young's modulus. Applying this, what will be the final expression? It will be half sigma square by E into A into L. A into L is the volume, and the final expression will be sigma square by 2E into V. This is the expression what we have given in case of resilience and proof resilience. And the strain energy in case of gradually applied loading will be equal to sigma square by 2E into V. This is the expression for strain energy due to gradually applied loading. Thank you.